Let's get back to our processing themes. So we talked about interaction on Tuesday. We talked about external libraries. I then realized that I probably should have told you guys what inheritance means in object-oriented programming, so we spent a little bit of time going over inheritance. Then we talked about user interfaces. We looked at Control P5 as one particular user interface. As I said, it is we're unfortunately sort of reaching that point now where in order to progress much further, we end up with a bit of a step up in difficulty. That is not unique of processing, it's sort of the same in most languages. Unfortunately, Control P5 is one of the examples where it's probably needlessly complicated. I feel like perhaps if they'd had less flexibility in it, they could have made it a bit more, this is how it has to work, and so design it that way, but they chose to increase the flexibility at the cost of having understandability, I guess, and that's a sort of common trade-off. But we had a look at a few examples. I showed you guys where to find more examples for Control P5, so hopefully if that's something you guys are interested in, there's lots of other stuff out there for you to look at. Otherwise, by the time we get to Unity, this will all seem like, you'll be like, why isn't it just this easy to do a user interface and everything? But it's always good to know what's happening behind the scenes as well. So we're going to move on to a few other, themes, and possibly we'll manage to get on to the next set of slides, which I think is graphics as well, which will be good because that is very applicable across all programming languages. But we're going to have a look at a few more things which are specific to processing. So first up, we're going to have a look at audio. So audio is, well, we all know what audio is, I probably don't need to explain it. But basically, we're looking at sound as being a wave of air pressure. This is a bit of, I guess, a bit arbitrary for what we're doing. We don't need to know the physics behind it, but it will hopefully sort of explain what's going on in some of the examples. So we think of sound as a wave of air pressure. Effectively, we have some speaker or something, and that has a little membrane which moves back and forth, controlled by a magnet, and that will send out sound waves by compressing the air. And there's various things which control what we hear from the sound wave. So there is the volume, effectively, is how much this air is being pushed back and forth. So if it's pushing back and forth, it'll move our eardrums. So on the other side, I'll draw, that's what an ear looks like apparently. Inside that you have your eardrum, which has a little membrane which is connected to some bones and stuff, and then there's some hairs. And as these waves come into your ear, they push this drum, which in turn does some other stuff, I'm not a biologist, and then blows these little hairs inside your ear, and these hairs vibrate at certain frequencies and your nerves pick that up. So depending on the length of the hairs will determine what frequency they vibrate best at, and if I'm wrong on any of this, feel free to correct me. And then you detect that nerve impulse, and your brain interprets that as I've heard a sound at this frequency. So there's a couple of things which can determine how we hear things. So one is the volume, or how loud things are depends on how much this moves back and forth. So if it's moving just a tiny little bit, it's not very loud. If it's moving a huge amount, it's moving quite loud. And likewise, this is a speaker, but it could be my vocal cords vibrating the air and so on and so forth. And the other thing is the pitch, which is basically how compressed together these sound waves are. So if they're compressed really, really closely together, they tend to be quite high pitched. If they're spread quite far apart, they tend to be lower pitched. Okay, so we don't tend to illustrate things that way. We tend to illustrate things when we're talking about audio with waveforms. So if we have a graph for some time, if we drew a wave which looks like this, this is basically a sine wave. So, if this was, well, if you plotted out the value of sine as you increase, you get something like this, and this would be like a single note for us that we would hear. And that is, there's the two things in here. We talked about the volume. So the volume is the amplitude of the wave. So if this gets larger, it gets louder. If it gets smaller, it gets quieter. So this would be louder, and this would be quieter. And the other thing we have is the frequency. This would be a deep low pitch, and this would be a really high pitch. So it's basically the compression of the wave determines the pitch. So this would be deeper, and if we just look at where a full waveform, so when it goes from 0 to its maximum to its minimum and then back, so maximum, minimum and back, that's one wavelength there, and that's one wavelength there, so this would be higher pitched. All right. So when we're talking about computers, this is a very analog signal. So when I talk about analog, I'm talking about basically an infinite number of values. I mean, practically it's not infinite, but for what it's worth, you know, I can't tell if I'm making a noise with my vocal cords. I can't say, well, let's decrease it 1/billionth of a, you know, piece of tension or whatever. So as far as I'm concerned, you know, within the vocal register of what I can do from low to high, quiet to loud, it feels like there's infinite. I could make it infinitely more quiet a little bit at a time. And you wouldn't notice like the stepping effect of it's getting quieter by a fixed amount. It just sort of goes in this nice smooth curve down. Realistically, in computers, we don't deal with infinite numbers because computers effectively boil down to binary. Everything is a 0 or 1. So what we could say in let's say we have a waveform here that we want to try and recreate. So we want to recreate that in a computer which has two values, a 0 and a 1. We could say, okay, let's represent this by 1, let's represent this by a 0, and we end up with a waveform which looks like that. And if you play that, it will sound awful. It'll be very abrasive because it doesn't have any nice harmonics or anything. It'll be like a very mechanical buzzing sort of sound. And we'll see some of these different in 2 slides time, I think. They're called oscillators. They're basically things which generate noise, and you can generate them in different shapes. So, okay, 1 and 0. If we look at it, we've got all this area under the graph, or around the graph, which is actually not a very good approximation. We want to try and get this looking as much like this curve as possible because that will give us the closest reproduction of sound, so it'll sound most like what we want it to sound like. So what we can do is instead of having 0 and 1, we can say, okay, well, let's do 2 digits. We have 0, 0, 0, 1, 1, 0, and 1, 1. So in binary, you can see this is just counting up. This is 0, 1, 10, 11, or if we were to write these out in their decimal equivalents, 0, 1, 2, and 3. And then what we can do is if we have our waveform like this, we could say, okay, well, let's make this 1, 1. Let's make this 1, 0. Try and put these sort of even. This can be 0, 1, and that can be 0, 0. And so then I might say, okay, well, let's sort of average this out for about that, it's there. For about that, it's there. That, it's there. That's there. Oh, that's not very even, is it? And what we'd find is if I had done a better job at drawing this, the areas we've actually got under the graph, or like which sit outside of the graph, will be slightly less than they were in the previous example. And so this would sound slightly better to us. And we can keep doing this. We could say, okay, well, let's add in a third one. Zero, 1, 0, 0, 1, 1, 1, 0, 0. And if we did this again and redrew it, we'd get slightly more accurate and slightly more accurate and slightly more accurate. But that's effectively what's happening when we do audio on a computer. We are trying to represent some waveform by basically breaking it down into these little steps. And we'll see some examples of that later on. But the reason that's important is because when we're basically trying to push sound out of our sound card, what we're effectively doing is that if we have some sampling time t, so if this is, say, 1 millisecond, and this is 2 milliseconds, and this is 3 milliseconds, what we're basically going to do is try and sample this as best we can, and then figure out the closest number to it, and then push that number out into the sound card, and that will move our speaker the appropriate amount. So yeah, sound is a wave of pressure. It has the pitch, which is the frequency, so how long or short those waveforms are, and we have the volume, which is the how high and low those the waves are. And we can basically approximate having a nice clean sound wave with an analog sound wave with a digital form by breaking it down into these numerical waves using what's known as discrete sampling. So we're basically trying to split it up and put it into some boxes which our computers can work with. Okay, so why would we, well, probably don't really need to cover this so much, but some uses, I guess, for sound as a feedback thing. So you can have an audio icon, so you get a text message, your phone makes a noise, you know, oh, that's a text message. So it's basically gets associated with something in the same way that, you know, a visual icon would. A little notification pops up on your computer, you've got a new email, your phone makes a dinging noise. Either of that you know immediately without having to actually give it any focus or any attention, this has happened. Aid simulation, so this is something that Rob's really interested in. You guys had the research rodeo the other day, so everyone talked about all that stuff. So Rob's interested in things beyond the visual side of virtual reality. So, you know, sound is sort of I'm not sure the exact numbers, but visual processing in our brain takes up by far and away the largest amount of processing based on energy usage of all our senses. I can't remember the next one, whether it's touch or sound, but it's very important to us. Like, you know, if you ask a lot of people what if you had to lose a sense, most people would say they would like to lose sight the least because we rely on it the most, but sound is usually number 2 for most people. Most people feel like they could probably get away with losing your sense of smell or taste or touch, but, you know, sound is really important for making things feel realistic. And as far as simulation goes, that's quite important for the sort of stuff we do here at the lab. So if you think about when you're dealing with digital experiences, I have having been on this earth for a few decades now, I have a certain understanding, expectation about the environment. I know, as I'm sure all of you do, roughly what this is going to sound like when I bang it on the table. You know, before I did that, it's probably fine. And that's because of our experience with, you know, this is probably wooden table and stuff like that. But you can really change the realism of something by just affecting the sound. Like you can imagine if I dinged this on here and instead of sound like that, it sounded like that. Your thoughts, or actually even better, something like that. Your thoughts would immediately be, okay, that table's not actually made out of wood, it's made out of metal. That's surprising. So these sort of little cues can actually be quite different, quite important as far as making a situation quite realistic. If I look around, everything looks perfect, but when I interact with it some way, it makes a sound that I wouldn't expect. It immediately changes our mental model of, okay, this table looks like it's metal, wood, but it sounds like it's metal. Why is that? Is that a mistake in my perception, or is that something that I have, you know, our simulation is not actively reflecting? Likewise, there's all sorts of things, you know, if you think about low quality TV shows and movies and stuff like that, with audio recording, you have a bunch of characters in a room and they've obviously overdubbed it. And, you know, in this room is quite a good example. It's quite small, we've got quite reflective walls. I can actually hear a little bit of reverb of my own voice bouncing off the walls, but if I'd have recorded this in a soundproof sound studio, it it would sound very different. And you often get that, like when you're watching dubbed things, that it doesn't feel right because they've obviously recorded in a different environment. So when we're trying to do simulation, you know, sound can vary. Even if you've got the most beautiful simulation in the world, if the sounds don't respond in the same way that the visuals do, or don't provide the same experience as the visuals, it can be quite jarring to the user and really throw them off that experience. Which I guess gets me on to the next point, telling information about the objects making the sounds. So the example of if I have something and I can bang it, even if I'm not allowed to touch it, like you could be on one side of the room, I could be on the other side of the room, or even if I'm blindfolded, you know, you could drop something and I could have a guess. It sounds like you've dropped something, probably plastic on something metal. But with that visual aspect as well, it really can help clarify our experiences and our expectations of things. Okay, yep, even without having the opportunity and the ability to interact with something, I can tell what it is simply by how the noise it makes and that sort of stuff. As an emotional trigger is something that horror movies in particular have done. They've really nailed this. So you watch a horror movie, more often than not, the things which will make you jump is the noise of the harsh violin screech and stuff like that. It's not actually so much what you're seeing on the screen, it's that audio thing where there's a very, your audio perception runs through a very deep like part of your brain, like a very primitive part of your brain, which can actually trigger emotions before you're even consciously aware of what's going on. And that's, a survival technique. If you hear something, like you're in the forests and you hear the cracking of a twig, you might immediately think, okay, there's something else out here with me. I need to run because I'm about to get eaten by a tiger or something. Yeah, and so that's very important as well. Like, we've got all these different sort of ways of playing with sounds to trigger certain emotions in people. And if you're looking at how digital storytelling and stuff like that, you can use sound really to your advantage to try and invoke certain feelings in people. You can scare them by having certain noises, or you can make them feel quite melancholic and nostalgic by having certain particularly music which is played in flat keys and stuff like that tend to bring out this melancholic sort of sad feelings, and the major keys tend to be more upbeat and happy and can trigger that sort of stuff. And even what I was saying before, a little bit of an aside, there's actually a really interesting theory behind things like ghost sightings and stuff, in that they've found, not in all cases, although they haven't probably studied them enough, but they've found in certain cases that places which are particularly haunted actually have certain acoustic properties, which means they have very low frequency audio, which is actually almost imperceptible to what we are able to hear, but the hairs in your ears and even the hairs on your arms and everything are able to detect this thing, and they bring out certain primal instincts in us. So there's one, for example, that I was reading about. It was in this place in the States, like an apartment building or something, and it had one of those big ventilation fans on the roof. But the fan was moving at a certain frequency, which is actually very similar to the low frequencies in a lion's roar. And so for people who are particularly in the basement of the building, because of the acoustics, they often perceive this feeling of dread and constant fear, and they get in there like, oh, this place is haunted. But really what was happening was this fan was actually stirring something deeply primal in people's senses. It was as the same sort of things of a large predator has in their roars and their behavior, that people, would kick off this experience that something bad is about to happen, and people would then start attributing it to, oh, this place is haunted. And there's other things as well. They've detected certain frequencies can actually play havoc with the fluid in your eyes and cause you to start seeing dark shadows at the edge of your vision, because it's causing the fluid in your eyes to start pressing on your retina. But kind of a bit irrelevant to what we're talking about here, but using sound as an emotional trigger is actually something which can be very potent, and I think probably in gaming and stuff like that is something that has become more prevalent recently, as people become sort of more aware of all these things we can use to affect people. And it can also be used as a product of play. Where's the remote before this blares out incredibly loudly? I left it over there. because I have no idea what the volume on the TV is. Well, actually I do because it was just dinging. So this is using sound as, rather than, I guess, an enhancement, as the core element of an experience. So this was something, I'm not sure if this one was done in processing. Yes, there is audio. But there have been similar things done in processing as to this. Does it say? Blah, 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 blah. Oh, okay, not so much, but that's okay. So the idea behind this is they're using some computer vision tracking algorithms with a cool little, so they've got a camera and a projector mounted above the table. They're using some computer vision to detect these blocks on the table, and each block has a certain aspect. So we can see things in here, like this square one here is basically outputting a square wave, which is like this sort of thing here, where we have boxes rather than curves. And you can see they've got a bunch of other shapes, so a nice sine wave in there. They've got, what else have we got? A saw wave and some other bits and pieces. Some of them are just used for playing audio. But the cool thing about this is they've got all these interesting interactions between these various blocks, such that when you move them together, you can chain them together and create like your own sort of synthesizer stuff. And you can rotate them to change the frequency and the volume and all that sort of stuff. So just sort of showing the interaction between them. So this is changing, you can see there, they're changing the wavelength. So the wavelength gets shorter, the pitch gets higher. Before they were turning that thing, it was increasing and shrinking the size of the wave, which increases and shrinks the volume. So we fast forward because it's a long video, but it's worth it. So by chaining together very simple audio effects, you can actually make some quite interesting sort of experiences. And the whole thing about this is basically an audio experience. Everything else there is just to allow people to more easily interact with audio elements. So yeah. Get some pretty cool stuff there. Just chaining some very simple sort of things together. If you know what you're doing, I would argue that this is going to be more art than science. And I have to say that because it's something I'm not particularly artistic in this room, and that's something that I can do. So, but it was pretty cool. So there's arguments as well for having audio as just the sort of motivator. We had a master's student here, I think one of our first master's students actually, who was from the School of Theatre and Performing Arts, and he was really into poi and all that sort of stuff, and put together a thing using a PlayStation Eye camera, which basically would track poi, and depending on how you spun it, would start generating music. So he was doing stuff like this, and basically depending on the speed you spun it would depend on the playback speed of certain things. You spin it faster and faster, and the music plays faster and faster, or you spin it larger, increases the volume. He then ended up throwing some training stuff in there as well. So you'd see a projector of yourself, like the camera in front of you, a projector behind you shining on a screen, and there'd be like various things on the wall that you had to spin the poi through. And it was quite a cool wee demo. He's now, I think he's working at Lincoln or Otago or something, but he still goes around. He's a festival guy, so he goes around all these festivals. He's managed to shrink his entire system down to fit into a little briefcase sort of thing now. So he goes to festivals and he pops it open and starts the software on the laptop, and he's got the projector and camera. It's quite cool. It's really interesting sort of example. Okay, so as far as sound and processing, there's a few different ways, or a few different things in there which allow us to do quite a lot of stuff. So there is the processing reference manual for sound, which is the sound library for processing. So this morning I thought I better check this out. So sound used to come installed by default in processing. It, for some reason, doesn't anymore. So you have to go into Add Library, search sound, and you'll see in there sound provided by the Processing Foundation provides a simple way to work with audio. and so you can just install that and have the sound working. Now, a bit of a caveat here, I suppose. I've found in previous MHIT courses, certain people's computers just will not run the sound library, and I don't know why. We have done assignments before, they built their own MP3 player, and some people just could not get it working on their laptop. So we're not going to be building an MP3 player for that reason this time round, but you're welcome to have a play with it. As far as I've been able to tell, in Unity all their sound stuff works regardless of computers. I think it's just a weird Java thing, so yeah, be warned that if it doesn't work, use a different computer. So you'll notice after we've done that, we can go import library, and it will appear in the top set, which is a little bit counterintuitive because all the other ones we install appear and contributed, but sound appears in that one. And likewise, when we were looking at processing the other day, clicking on import library will bring in import processing sound, and then we can start, doing some stuff with the sound. So there's three main sort of classes, three main things. There's audio device, which allows us to do some stuff with the hardware access, so we can choose what sound device we want to use, whether it be a microphone or a speaker or whatever. And then there's the two main parts of audio is obviously output and input. We're either playing some or making some noise or listening to some noise. So in output, the one that people most commonly use is sound file, which basically allows you to load a file. I think it supports, if we go back to here, I think it supports WAV, AIF, and MP3. So, you've got a few different formats there which work. And then we've got a bunch of various generators. So these are things which allow you to create noise based on mathematical formula and equations. So you have oscillators which can produce sine waves and square waves and saw waves and triangle waves and all that sort of stuff. You can have noise generators which basically just create waves which are just random, and so they make noise. So you're probably familiar with things like white noise, which is that sort of TV static. If you turn on your TV and you're not tuned to a channel, that's white noise. But there are other noise. There's pink noise and brown noise and grey noise and stuff. And then for input, we have the audio in class, which provides a bunch of high-level methods to record sound. I'm not sure why player's in there. So audio in provides a bunch of examples to record sound. So we're going to have a look at some examples. So starting with audio output. So you'll notice in some of these slides I have down the bottom here what kind of look like paths, and they point to examples. So once you've imported the sound library, and I actually had to restart processing to get this to pop up, if you go to examples and then close some of these up, you'll notice that we have libraries and then sound, and if I open that, we'll see there is a sound file, and then in that folder, finally, there is simple playback. And if we open that, this is basically what some of these ones are looking at. So let's close that and slide this over here. So if we want to play a file, all we have to do is say sound file. So sound file is a particular class. So we're going to create a new sound file object from that class. Awesome. Undo is not working for some reason. I have a feeling the keyboard on my laptop's past its best by. So we create a new object of class sound file, and we basically say new, so call its constructor. Again, we have this thing that we saw in Control P5, so we're passing an instance to our program to allow sound file to do any callbacks that it needs to. So hook itself up to the draw method, for example, so that it can update the sound. And then we have the name of the file. So in this one here, we have, you'll see that more or less that exact line of code. They've declared sound file up here so they can access it the whole program, but down here we have sound file equals new sound file, this vibraphone.aiff. So if we go into sketch, show sketch folder, you'll see in the data subfolder that there is this vibraphone.aiff, And if I open this in something that can play it. So this is basically the AIFF file, so it's like a compressed audio format, and this is what it sounds like. So what this program is going to do is it's going to load this sound file, and then it's going to tell it to play it in a loop. So there are two options. There is play and there is loop. Play will play the song from the start, or the sound file from the start to the end. When it finishes, it will stop. Loop will play it from the start to the end, and when it finishes, it'll start back at the start, and it'll keep going until you explicitly tell it to stop. So if we run this code, turn that up, so you can hear that sound file playing. So there's a few other things which are going on in here. So we load the sound file, we tell it to play in a loop. In the draw method, there's a few additional things which go on. Let me just silence that for a second. So you can see we're doing three things to the sound file. We're calling .rate on it, we're calling .amp on it, and we're calling .pan on it. So these three things, rate changes the speed of the playback. So as 1 is play it back at normal speed, if we play it back at 0.5, it will play back at half speed. If we play it at 2, it'll play at twice speed. We have amplitude, which is the volume. So as 1 will be max volume or normal volume. If we go 0.5, it'll be half volume. If we go 2, it's twice volume. And panning is which speaker it's coming out of. And it's, unless you go and stick your head up against the screen, you probably won't notice it. But if you do these examples wearing headphones, you notice as you pan, you can hear it move from one side of your head to the other. So panning is good when you're sitting directly in front of the thing, or you have some sort of surround sound, or you're wearing headphones. Probably not going to be too noticeable here. So what we call these rate, amp, and pan functions with, you'll notice we have these playback speed, amplitude, and panning. And there is a function here called map. So map is actually quite a useful function, probably one of the more useful ones I've come across in processing, and no other language has it by default, which is a bit of a shame, or no other language that I use with any regularity. But what the map function does is it has 5 variables. So it has in, which is a value you pass in, and then it has in max and out max, which is the minimum and the maximum that value is likely to be. It can go inside or outside of those, but this is basically where we're going to assume it to be. And out min and out max will be the value that gets returned by this function, and it's basically going to map this value in between this range to this range. So for an example, if I had something like map 0.5, 0 to 1. So basically I'm saying the in value is 0.5 and the min and the max are 0 and 1. So in this case 0.5 is halfway between them. Let's map that between 0 and 100. So what that's going to do is it's going to say, okay, where does this fall between these two numbers? Well, it's at halfway. So in this case, the returning value should be halfway between these two values. So in this particular example, it would be 50. Or if this was something like 0.25, this would be 25. And these numbers can be anything. So I could say, let's do this between 10 and 20. And now this will be, if this is a quarter of the way between these two things, it'll be a quarter way between these two things, which will be 12.5 from memory. So it's just a really nice sort of helpful function to map a number between one range to a number between another range. So we can see in these examples here, what they're doing is for the playback speed, they're mapping the mouse X position, remembering that if we have our screen like this, mouse X will be our position somewhere along the horizontal axis between 0 and the width of the screen to 0.25 and 4. So basically what we're saying is that this will map to 0.25 and that will map to 4. So if our mouse is at the far left of the screen, playback speed will be 0.25. If it's at the far right of the screen, it'll be 4. If it's in the middle, it'll be halfway between those two numbers, which is something that I can't figure out off the top of my head. But basically, it's allowing us to map the left-hand side of the screen 0.25. The right side of the screen is 4, and the middle will be, well, everything between that will be the same fraction. So if we run this example again, and I turn this up so it's loud enough for us to hear. So if it's very low, very far left, you can hear it's playing really, really slowly. So that's playing at 1/4 speed. So that's, I don't know, around 1-ish. And then as we go more and more to the right, it's playing faster and faster until we get to the far right of the screen. Now it's playing 4 times the original speed of the file. And you can hear it just finished then, and now it's restarted again. So we have the same thing for amplitude. Amplitude maps the mouse's Y position from 0 to height, and it's going to, 0, okay. Amplitude is mapping the mouse Y position between 0 and width, which doesn't actually make any sense. So let's change that between 0 and height. And it is changing, it's going to map that so when the mouse Y is at 0, so at the top of the screen, it's going to be 0.2, or so 20% the volume. And if it's at the bottom of the screen, it's going to be 1, which is maximum volume. So hopefully, no, other way around, sorry. So when it's at the bottom of the screen, it's going to be at 0.2, so barely audible. And then as I move up to the top of the screen, it's going to go up to the maximum value of 1. Why that was width originally, I don't know. I suspect that was probably a mistake in the example, so feel free to just assume that's height. Likewise, they have the panning, which is actually possibly why that sounded a little bit weird. I'll just comment that out. Yeah, so that's how it should have worked. So it's at 20% of its volume at the top, and then as we move it down, it gets louder and louder. What I think we'll find is that the panning, which is whether it comes out of the left speaker or the right speaker, so only one of the speakers is working on this TV, which is why it's getting quieter, or possibly through the sound capture or whatever. So we can hear it. We can hear it quite loudly when it's coming through, when it's set at -1, which is probably the left speaker. When we try and move that down to the right speaker, it's going quiet. So I suspect something between here and the TV is only sending through the left audio channel. Okay, so playing a sound file. Create a new sound file with the name of the file you want to load. Call play to play it. Call loop to loop it. There are a bunch of other functions you can use on sound file as well. You can jump to a specific position. You can pause it. You can figure out how long the duration is. You can stop it. We can tell whether it is playing or not. So there's a bunch of other functions in there that we might want to play around with. And we can control its speed with rate. We can control its amplitude with its volume with amplitude, and we can use pan to move from left to right. So that's the main way of generating audio. It's usually much easier to create the audio beforehand, so record something with a microphone or whatever, and then play it back. But if you do want to create audio from scratch, you can use, like we saw in that example, you can use things like oscillators and generators. So if we open the oscillators subfolder, so libraries, sound, oscillators, you'll see there's a bunch of different sound files in here. So if I open sine wave and we have a look at this, so you'll see most of these oscillators have some name OSC, the oscillator. So in this case it's a sine wave or a sine oscillator. So we've set that to a new sine oscillator, again passing in this, and we just call play. we don't need to call a loop on oscillators because they effectively are just one wave anyway. So if we played it, it would be over almost instantaneously. So we call play, and that will keep playing it. This one has the same sort of thing. We can pan left, pan right, or move the mouse left to right to change the frequency, move the mouse top to bottom. So you notice it is actually height this time, not width. And let's pull out panning because this TV doesn't work right. But we can play a sound away. This is a sine wave. So as we move left to right, it's changing the frequency. So it's changing it from, as we move left to right, something which looks like that, to something which looks like that, to finally something which looks like that. And that ends up changing the frequency that we hear. So it starts very low pitch, and then it will get higher and higher and higher pitch, and volume from bottom, from quiet to loud. So that's a sine wave. There are a bunch of other waves in there we might like. So square wave is the other one we've looked at, which is just when we draw squares effectively rather than that. And you'll hear it's a much more abrasive metallic sound. It's not a sort of smooth and is quite kind of very 1980s like video gamey sort of sound effects because when you're talking about like these 1980s games which didn't have a lot of memory, you didn't want to have to assign, you know, a ton of memory to do a simple sound. It's much easier to say play. Push a 1 out and then a 0 out, so they could play the, you know, often use these things to save on memory. There are a bunch of other ones. So a triangle wave is, as you would expect, a triangle is slightly warmer sounding, I guess, than a square wave. It doesn't have the, it still has sharp edges, but at least they're sort of on a line rather than straight up and down. So not quite as kind of awful sounding as the square wave. We've got a saw wave, which actually, let me just so this is the saw wave here. So it looks like, whoops, a triangle. Was that one there? Yeah, here we go. So a triangle wave looks kind of like one of those, but if you drew it with sharp lines. A saw wave is more like teeth on a saw. So it goes up and then it has the abrupt drop down. So if you think about it, this is quite a smooth sort of sound. That is a smooth-ish sort of sound. This is a very abrasive sort of sound, and likewise, that is a very abrasive sort of sound. So it's more to do with how we chain, like the transitions in the waveform depending on how it sounds. So this is quite smooth, this is quite smooth. Because we have this, you know, immediately going from a 1 to a 0, it's quite an abrupt sound. Same thing here, whereas this is sort of going from a 1 to a 0 on a smoother angle, likewise, that one there. So saw waves and square waves are less pleasant to listen to than the other two. Where's processing gone? Yeah, so we have saw wave, sine wave, square wave, and triangle wave. We also have pulses that we can push out. So a pulse wave oscillator. I'm not 100% sure actually what that looks like because it's not a common one, but we have it looks like possibly like a square wave again. I'm not sure, but again, it wouldn't be surprising because that's not a particularly pleasant sort of sound. So we can generate all those sounds and we can add them together as well. So when we're talking about, if we were to draw out sort of, obviously these are all like one frequency, so they just are one noise. If we were to play back how my voice sounds, for example, would probably find that it looks something like this as I'm talking, and that can actually be broken down as adding a whole bunch of various waves together. So you might say, okay, we can approximate this by having an initial sine wave, and then maybe we'll put a more high frequency sound wave into something, and that will, if we add those two sine waves together, we're going to get something which sort of goes like this. And so we can start having all these various waveforms that we add together to, again, try and approximate this shape. And that's exactly how things like audio compression work. So if you compress something to an MP3, what it's trying to do is find a bunch of, rather than representing each of these as numbers, so if we say this is 0, and this is 1, and this is -1, or rather, let's say that's 1 and that's 0, rather than like we did before, and we said, okay, well, if we do that, we end up with quite a sharp wave, so let's make that 0, 0, and that 1, 1. Oh, that's still not close enough, 0, 0, 1, 1, 1, and keep on adding more and more bits to it. We could basically just say at time t, let's make that time 1, the value is equal to 1, 0, 1, 0, 0, 1, 1, 0, and then at time 1.1, it's 1, 0, 0, 1, 0, 1, sort of thing. We can record each of those values at each point in time and play them back, and that will give us a perfect rendition of the sound. And that's basically when you have a wave file, that's basically what's kind of being stored in there, the value at each point in time. When we try and compress that down, what we're trying to do is find a bunch of wave files, or sorry, a bunch of like waveforms that we can try to approximate what this looks like. So there's a bunch of things, what's it called, I think the Taylor series. Which will basically add, something like this. So we have if we have a 100 hertz frequency wave and a much smaller 50 hertz frequency wave, when we add those two waves together, we end up with something like this. And you can imagine if we kept on adding more and more waves together, we'd end up with, we could sort of recreate any of these shapes as long as we sort of said, okay, add this this wave for, 0.2 seconds here, add this wave, or add this wave from 0 to 0.2 seconds, add this wave at 0.4 seconds, whatever. We can actually start to approximate these waves. So theoretically, you could do the same thing with this. You could start adding various waveforms together and to try and create different sounds if you want. So I think this is, so this is sort of doing, this example sort of does that. It takes a bunch of sine waves and tries to add them all together to end up with something more than just a single frequency. How do we control this? Frequency detune. So, I mean, still not quite as obvious, but if you listen, you can sort of pick out there's at least two frequencies in there. There's a higher pitch one and then there's one a bit lower. As we move from what it looks like in here, as we move the mouse from left to right, it will try and bring them back into tune. So you can hear about there, they're about the same sort of frequency, but as I move you can hear one sort of stays where it is and one gets higher and higher frequency as we go. So there's always that sort of background hum, and there's one which is moving, although apparently there's actually 5 sound waves in here, and that's just changing the frequency of all of them. So yeah, you can add them together. Obviously that is quite difficult unless you're like that person who was playing with the reactables thing before, so I wouldn't recommend that. It's probably much easier to record your sound. But there are other things in there. So we talked about noise generators before. So processing has some noise generators. So there's a white noise generator. Again, the class is called white noise. Create the object, white noise this. And we can change the pan and the amplitude. So white noise, brown noise, and that, they're all generated with different sort of like random number generators, effectively, and they all sound slightly different. So this is white noise that is probably most familiar to most people. So TV static. There are other ones. So brown noise is a little bit more bass from memory. So like waves crashing on the beach. And I think pink noise is kind of between the two of those. Can't even really hear it very well, but you know, not quite as harsh and abrasive as white noise, but not as bassy as brown noise as well. So there are various things you can do to generate, you know, audio thing, but realistically, most people are just going to play back a sound file because that's the easiest way to deal with it. Let's actually do audio input and then we'll have a break because at least that way we can finish a topic. So putting audio out is one thing. We can also support audio input. Again, this is something that I have noticed tends to work better or worse on certain people's computers. So it may not work for you, but under Libraries Sound I/O audio input, there is a nice example which does that. So we have audio in, which is audio in class and input. So we're going to create a new an input thing, a new input object of audio in. This again, and this 0 here is basically saying what device it should be using. So you can usually leave this as 0. If it doesn't seem to be working, try changing that value in there. Most laptops will have one microphone in it, which is usually with the web camera. But if you plug a different microphone in, or if you plug a web camera in, a different web camera or whatever, and something with its own microphone, you might need to change that number to get the audio from the different device. And then we just call input.start, which will start the audio capture. So the other thing in this one, so calling audio input will start recording audio, and you can get that audio. Where are we? You can get that audio out of the audio input. Can we? No, we can't actually. I tell a lie. So what you have to do is you have to have an audio analyzer like Amplitude, which will get you the basically takes the audio input and does some processing on it. I thought there was a way to do, yeah. So there are two ways of doing audio input there's two ways of processing the audio input. You can do the Amplitude, which will just tell you how loud something is, and then there's FFT, which stands for Fast Fourier Transform, which will break down the audio into bands and allow you to analyze that. I thought there was a way to get the raw audio, but I know there is in Unity, but apparently not in processing. But anyway, so we create a new audio input object, we tell it to start, and then we create a new, you see here we have this amplitude class and we have this loudness variable. So we're going to create a new loudness object or amplitude object and assign it to loudness, again passing in this. And then we use loudness.input to say that, so input is an analyzer, or amplitude is an analyzer, sorry. We say use the input from that, should be coming from this audio in. So we have input, the input variable is an audio in object, and we pass that into loudness. So that loudness will now start getting data from the audio in and processing it. So in our draw method, all we're doing is, again, we're mapping the input level, so that's just going to change the amplitude in that. So as we move the mouse from top to bottom, it'll change how loud that processes it. And then we called loudness.analyze, and that will return the volume at the current point in time. And then we calculate the size by mapping that, and we draw an ellipse. So let's run this and hopefully it will work. So yeah, you can see here there is a little pink circle, and that pink circle is being drawn based on the loudness. So this loudness analyzer is taking in all the audio and it's basically outputting one value, which is just the current, or how loud the current thing is, what the current amplitude is. So I can change this, I can move my mouse from top to bottom, and that will change. There's this loudness.amp, which is the amplification. So as I move down towards the bottom, it's going to amplify it more. So theoretically, if I move this towards the top, it doesn't actually seem to be making that much of a difference, but should be slightly smaller circles at the bottom compared to the top. Yeah, and so that's basically showing what the microphone is picking up. So as I talk louder or click my fingers, you can see the circle gets louder. If it's quiet, circle is very small. So that's a very simple example, and you can think of it as like a one-dimensional sort of thing. If you want to create some game or something where it depends on how loud the person's talking, or you have to clap your hands or something, you could simply measure the loudness, and if the volume is over some threshold, you can say, okay, that is likely to be, whatever we're looking for. So the other thing, I'll throw this in here as well actually, is fast Fourier transform. So fast Fourier transform is basically tries to, from a waveform that comes in, tries to break out the various, so we looked at this example here where we could make up a sound wave by various waves. What a fast Fourier transform does is it tries to do the opposite of that. So it tries to figure out the sort of wavelengths that would be required in order to make an audio sample. And because the wavelengths that we add together tend to be, we'll add this waveform and this waveform together, we know that the difference between these two waveforms is this one, because it has a much longer wavelength, is going to be much bassier or have a much lower pitch than this one. What the fast Fourier transform allows us to do is effectively allows us to break out these various waveforms based on their pitch and the relative volumes. So if we run this example here, so this one's just playing an audio file back, but we can see this visualization here is being generated by the fast Fourier transform. And so down the bottom here we have the lower wavelength, so it's calculated that there are some lower wavelength waves which go into making up what's being played out here. And so that's left to right is the pitch of the waveforms, and top to bottom is their amplitude for how loud they are. So this is quite a bassy sort of song. So you'll notice that there tends to be a lot of representation in the bass. There's not a huge amount in the higher pitches. There's not so much there. So theoretically we could, let's give it a try. Let's change this. So this is taking a sound file. There's a bunch of stuff in here which is set up to do rendering, but it's taking a sound file and it's looping it, and then it's creating a new fast Fourier transform, and it's using that sound file as its input sample. So let's take our example before, which did audio input. Instead, I have no idea whether this is going to work, but we're going to find out very shortly. So we're going to, instead of having a sound file as our sample, we're going to have an audio input. Or audio in, sorry. We're going to comment out everything which loads and starts playing the sample, and instead we're going to start our audio input, and we're going to pass that input into the fast Fourier transform. And hopefully, if this works, we now have a waveform which is basically showing my voice. So you can see there's still majority, at least in this fast Fourier transform, the majority of my voice tends to be bassier. That's not because I'm Barry White and have a super deep voice. That's just there is a limit of vocal range that humans can make. So, if we had an opera singer here singing at high pitches, we'd expect to see a lot more in the higher range. If we did have Barry White, we'd probably see less of, you can see this sort of tailoring down. His voice would probably be much lower in the spectrum. And it isn't like this value here is 0 either. This will continue on bassier and bassier. It's just in this particular example, they chose this as the cutoff as being the leftmost point. So if you want to have a try at this, try and sing your highest note or whatever and see how high up the scale you can get. We can have a little contest if people want, see who's MHIT's next great opera singer. But otherwise, let's have a break there, and we'll come back in about 5 minutes or so. Alrighty, so let's start back. So did anyone have any questions about the audio stuff? So unlike the Control P5 stuff, I think the audio stuff is actually not too bad because it's pretty simple. There's only like a handful of things you can do with it, and it's pretty controlled. Like this is exactly how you work with it. There's no, you can do it this way or that way to make it quite confusing. So there are examples there, and you can do some quite interesting stuff. I think more so than anything, the challenge with audio is trying to figure out how best to integrate it in whatever you're working on to create the experience that you're wanting to create. There is a whole bunch of other stuff that processing doesn't really do, or at least not the native sound library. You know, having things like 3D positional sound, having sound effects, or rather not sound effects, sound filters, so effects on sound, so having it sound like something, a thing is being played in an echoey room, or you know, a footstep, changing a footstep from sound like it's standing on you know, a carpeted floor versus a metal grate versus gravel, that can be done in things like Unity, but you know, again, this is more an introduction for you guys to these concepts and techniques that will then hopefully help you when we get to the Unity stuff anyway. Okay, so the last thing we're going to talk about, which is specific to processing, but again, all of these things are true of any language development environment, the theory behind them anyway, is communication. So when we're talking about communication, we're talking about communicating between two programs, effectively. So these programs could be running on the same computer, so you could have two processing programs running on your computer, or they could be two programs running on separate computers. So I could have, you know, a program running on this computer, another program running on the computer, or I could have a program running here, running on LJ's computer, and they're communicating with each other, or I could have a program running here and a program running on the other side of the internet. And because of these networking communication protocols we're using, they all work in exactly the same way, regardless of whether they're on the same computer, separate computers in the same room, or computers separated by other sides of the world. So we're going to look at two methods of networking in particular, TCP and UDP. So these are sort of the two standards which still are in heavy use around the world. There are other ones as well, but certainly nowhere near used as much as these two. So TCP stands for Transmission Control Protocol, and it is a reliable way of making a connection between two programs. That includes things like error checking. It has a connection so that you establish a connection, and then you know that connection is going to remain and exist for you. But it tends to be quite slow, and slow is a very relative term. I mean, we're still talking about things traveling at messages traveling at mostly the speed of light. But because of this error checking and stuff like that, it can potentially be slower than UDP. So I often, well actually let's talk about UDP and then we'll talk about the difference. So UDP stands for User Datagram Protocol. It doesn't have any error checking. So if you send a message and something gets corrupted in it, UDP has no way of knowing, whereas TCP will say, actually, you know, this message got corrupted, so perhaps when you're sending it through the internet, like it went through a dodgy router or something and some bits got corrupted, or it went through something and then the power got switched off, so only half the message got sent. TCP will detect that, UDP won't. The UDP is much faster as a result. You basically just send stuff off and hopefully it might make it. There's no guarantee that it will. But it does mean that it's faster than TCP because it doesn't have all these extra layers of protection and stuff and making sure that it gets through. And UDP is more or less connectionless. So you still need to have two computers communicating to each other. But TCP, and this is kind of, I guess, where the example comes in. I think of TCP like in the olden days when you used to call someone on the phone. This is before even I existed for the most part. I'd call someone on the phone and there'd be a switchboard operator who I'd pick up and I'd be like, I want to talk to LJ. And the switchboard operator would say, okay. And they would make a physically plug my phone line into LJ's phone line, and then we would talk to each other. So we would have a physical connection between the two of them. So like TCP, it's reliable because I get my own communication channel. There is a connection, like I have to physically set up that connection, or rather the switchboard operator sets up the connection, but the connection is made. There's error checking in that if LJ says something I didn't hear, I can say, sorry, can you repeat that? I didn't hear you. And so we have all these sort of aspects that TCP does. And a lot of these things work in the same way. So if you make a TCP connection to a program running on another computer, it will it'll contact the other computer and say, I would like to make a connection. The other computer will message back and say, sure, here are some things about this. Here are some things I'll accept. The connection needs to be a maximum of this length and blah, 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 blah. And then my computer will send back and say, yeah, that's fine, okay, I agree to that. And the other one will say, okay, and then they will gradually synchronize, and then they'll send a packet, or it'll send a message, and then the computer on the other end will send back a message saying, yes, I received that message, I'm ready to receive the other one. So there's a lot of back and forth, but that's basically what sets up that connection and makes sure there's error checking. And like each message that I send will have a little checksum code, and if I do some math on that message, so I add all the numbers up and divide by 13 or whatever, it will match that checksum. So I can say, oh yes, this came through correctly, or no, it's been corrupted. UDP, on the other hand, is like sending a postcard. So sending a postcard, I don't have to make a connection to you guys. If I'm traveling overseas and I want to send you guys postcards, all I do is write your name and address on them, stick it in the mailbox, and off I go on my merry way. There's no error checking. If I am traveling through the densest parts of Eastern Europe and it's particularly dodgy post office, I put my thing in there. There's no guarantee that that postcard is ever going to make it to you guys. Or likewise, if I'm traveling from a country with a poor mail service into a country with a good mail service, so I send my first postcard in the bad country and then my second postcard in the good country, there's no guarantee that you guys are going to get them the bad country one first and then the good country one. They might arrive the other way around because one has a better postal service. And likewise, UDP has that same thing. I will send you guys, or send messages to a computer. There's no guarantee they're going to get there. There's no guarantee they're going to get there in order. There's no guarantee when they get there, they're not going to have been changed in some way. It's not like it's a postcard. Anyone can write anything they want on the bottom of the postcard. So UDP is much like a postcard in that sense. It's much faster for me. I don't have to sit down, call up the phone, wait for you guys to answer the phone, pick up, make that connection. I can just be walking past post box and throw my postcard in there. So it's very fast to send. It's a little bit different in the post. Well, the example falls apart in that UDP will generally be faster the whole way through the sending process, whereas TCP is quite slow. Whereas a phone call, once I've done all that setup and everything, it tends to be quite fast. But that's sort of an analogy that I use that I think sort of illustrates the difference between the two of them. But one thing which is common for both TCP and UDP is they typically need a client and server pair. So when we're talking about clients and servers, really what we're talking about, a server is a program which is listening. So it's sitting there waiting for something to communicate with it. So that could be waiting by the phone, or it could be waiting by the post box. And then the client is the person who makes the call, or who sends the postcard, or the program who makes the connection. So in processing, we have this net library. So if I create my new processing thing, if I go sketch import library, you'll see network, and if I click on that, it will import processing net. So this is the library that contains all their net code. I'm not going to bother writing any examples because there's some quite good ones which run on here. So under libraries, network, shared canvas server, and shared canvas client. So libraries, you'll see there's shared canvas client and shared canvas server. As I mentioned, we need a client and a server. So we have to open both of these examples for it to do anything. Oops. So that's the server and that's the client. And now hopefully if I run the server first, so we run the thing which is waiting, and I run the client afterwards, anything I draw on the client you'll see should appear on the server. Right, so let's have a go. Who has this example open on their computer? So if somebody wants to open the shared canvas client. And let me know when you have. I don't know, again, whether this is going to work or not, but we will try. Who's got it open? Yep. Okay, so if you scroll down until you see new client equals this 127001 and delete 127001 and put in 10.34.54.17. So that's 10.34.54.17. 10.34 dot, what did I say, 54, yeah, 34, 54, 17. Yep, 10.34.54.17 and hit run. And try drawing something on your screen. There we go. So now it's not just running on the same computer. Gonzalo is drawing stuff on his screen. It's appearing on my screen. And likewise, this could happen. This could be running on computers on the opposite side of the world, and it would work in exactly the same way. So I don't know if I should close that down before he starts writing rude words on there, but so basically the way, if we have a look at these two examples side by side as best I can with my limited screen size.
Can we all be sharing the same?
So I don't know about this program. I have a feeling that there is another example in there that supports multiple people being connected at once. So if we have a look at it, the way processing does this is unfortunately a bit weird and confusing, and I'm going to do my best to explain it, and hopefully I'll do a good enough job. But basically, this is our server program on the left, and this is our client on the right. So in our server, we have the server object. Just ignore this client for the moment. Let's just focus on the server. And on our client, we have this client object. If we scroll down here into our server, you'll see that there's a ton of stuff that I'm not really that concerned about looking at. But in the server, we have S, which is our server variable, or our server object. New server, once again, this. And the number 12345. So 12345 in this case, or the second argument in the server constructor, is the port that it should listen on. So just as if I sent mail to you guys' houses, if you guys live in a flat or you live with your family or whatever, and there's multiple people living at one home, I can send a piece of mail to that house, but it doesn't actually tell me or tell the receivers who it's supposed to go to. So on computers, it's the same thing. Every computer has an IP address, ideally. And that IP address should be unique to that computer. But we only get one IP address per computer, and I could be running 100, 1,000, 1,000,000 programs on my computer. And each of those might want to be able to do something on the internet. So I might have Spotify running, streaming some music. I might be chatting on, Messenger or something. I might be looking at a website looking at Google in a different browser. And so each of those are effectively their own separate program running and doing communication over the internet. So what we have is, in addition to an IP address, which represents a computer, we have a port, which represents a specific program running on the computer. So in this case, we've said, I want to listen to port 12345. There are a bunch of standard ports which exist. So things like an HTTP server always listens on port 80 by default. FTP always listens on port 21. Email is, I can't remember, I'm pretty sure secure email is 221. And there's a whole range of them. So usually people will start in the thousands, just because there's a whole bunch of, in the first 1,000, there's a whole bunch of ports which are reserved. So it's usually a good idea to start with a number in the thousands. In this case, they've chosen 1234 because it's nice and easy to remember. So on the other side, in our client, just in the same way, we have C equals new client, again passing in this. And now we have two numbers. So we have the port, which is the same, 12345, which is the second thing. And the first string here is the IP address for the computer. So as I mentioned, every computer gets an IP address. It's a little bit complicated when we talk about networks like our university. So if I go to whatismyip.com, this tells me that my public IP is 202.36.179.109. That may or may not be the same for you guys because we are all connecting to the internet through the same connection. We're all using the university's internet connection. And once you sort of get to that level, things get a little bit complicated because the university wants to make sure that they have control over the network so that they don't get like viruses and firewalls and spam. So they have a bunch of IP addresses and then they can choose to assign them however they want. And you can have things which sit on top of IP and TCP which allow them to have one IP address and then it connects out. Like your home internet connection, you will have one IP address for your home internet, and then you might have your laptop and your cell phone and your Chromecast and your smart TV all connected to that one internet connection. So you have one IP address to your house, but then inside your house you have a bunch of different IP addresses, and your router is responsible for figuring out this piece of data is supposed to go to that machine, and literally routes traffic. That's where the name router comes from. Whoops. So in this case, there is a bunch of IP addresses. So the IP address I gave to Gonzalo before, I looked up. That is my local address, which is in, well, actually we can find it on whatismyip.com. My public IP, so this is the IP that computers on the internet see, is 202.36.179.109. But my local IP, which is the IP address that my computer knows that it has, is 10.34.54.17. So that was the address that I gave Gonzalo before, and that's in, I looked it up, there's a separate program, I can't even find it in here now. Oh, there it is. So there's a separate program here which will tell me the list of all the addresses my computer has. So my computer at the moment even has two addresses, one which is local, so all of you guys can communicate with it, but people outside of the university won't be able to. And then there's this address which people outside of the university can communicate with, but that may not specifically be pointing at my computer. That might be pointing somewhere else at a router, which then figures out where it goes. But there are a bunch of special addresses as well. So there is this address 127.0.0.1, which is also known as localhost, which always points at the computer that it's running on. So if I told my computer connect to 127.0.0.1, it will connect to itself. If LJ does that, her computer will connect to itself, and so on and so forth. So all your computers, when they are told 127.0.0.1, they know to connect themselves. So in this case, we're starting a server on our computer, we're listening on this port, and in the client, we're creating a client and we're connecting to localhost, so we're connecting to our own computer, and we're trying to connect to the program which is listening on port 12345. Then we have our draw functions. So in the client, it will basically detect some draw stuff. So it's using, we've seen this code before, line, p mouse x, p mouse y, mouse x, mouse y. And on the client, so you'll notice here, so the client is C, we have c.write p mouse x plus space plus p mouse y plus space plus p mouse x plus space plus mouse y space. So it's basically the same code that we're using to draw the line. We're actually calling c.write, which is sending that information out over the network to the computer that it's connected to. In the client, we then check c.available. We'll basically ask the client object, is there any data waiting for me? If there is, we call c.readString to get that data, and hopefully it will be in the same format, p mouse x plus p mouse y plus blah, 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 blah. Then we use this input.substring with this new line character. So basically what this is trying to do is each of these messages, we'll notice at the end, has a new line character. So each of these messages will be sent as px space py space x space y new line. So I'll throw in some numbers, say this is 10 by 10 by 12 by 10 new line, and then the next message will get sent straight after that. So it'll be 12, 10, 12, 10, 14, 10, new line, 14, 10, 18, 10, new line, and so on and so forth, because there's no guarantee that, like, when we send these messages out over the internet, they all get sent out, but then they all get concatenated together at the other end. So we just get a massive long stream of data coming through the other end. And so it's our job to separate that into the various messages which come through. So by adding this new line character at the end that we can see here, the very last thing we add to our right is this new line character. What that means is that then when we get our string, input read string, it will read all of this in one go, if it's all there. So what we do is we say, okay, let's just get the substring starting at index 0, so starting at the very start, and going until it hits the index of new line. So it's going to start at the start of the string, and it's going to keep on going until it hits a new line. So it's going to go do 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 do. Okay, let's just grab that part. So input will be 10, 10, 12, 10. And then we have the split method, which is going to split each of these up, because these are each, there's a space in between all of these. It's going to split all of these up and store it in data. So data is going to equal 10, 10, 12, 10. So split will return an array. So in this case, we're splitting it based on the spaces, and we're storing that in this data array, and then we're drawing a line, data 0, data 1, data 2, data 3. So we send some data out, we check to see if data's there. If so, we try and read out what we can, and then we draw that line. So just as Gonzalo could draw my screen before, I can draw my screen and it would appear in his window as well. Okay, so then we have the server. The server, and the way this is handled in processing is a little bit confusing, unfortunately. But basically what we have is we have the server, and then we draw a line on our screen, and like we had c.write in our client, here we have s.write, so we will write out mouse x, mouse y, blah, 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 new line. So, and I don't know why they chose to do it this way, because it just seems more trouble than it's worth. C.available will return a number, how many characters there are waiting for us. So if it's 0, there's no text waiting for us. If it's more than 0, there's some text. S.available will return a client. I don't know why it does it this way, it just does. So it returns a TCP, like a client object, and then we can check to see if that client is null. Null is a special keyword, which means it doesn't exist. So it points to memory which hasn't been set up. So we call s.available, and it will return a client, and we can check to see if that client exists. Is it an actual client or is it null? And if it isn't null, so it does actually exist, then we have exactly the same code in the server. So we call c.readString, we break that down, and we draw some lines. So in our client, the things to pay attention to, we have our client C, we set up a new client with an IP address and a port. C.write will send some text. C.available will return a number of how many pieces or how many characters there are to read. C.readString will read an entire string. On our server, we have the server S. We create that with the port to listen to. S.write will write some text. S.available for some reason returns a client, and then we have to check to see if that client is null. If it's not, then we can call c.readString and process that text. All right, so to summarize that, so the net library I haven't mentioned yet, but it uses TCP. We have client and server. So the server, we need to provide a port. The client, we provide the IP and port. For the client, .available will return the number of bytes or characters. The server returns a client to access data, which will be null if there's no bytes. So we've looked at the read string. There is actually a bunch of other methods we could use. So there's read, which will read a single byte. Char, which will read a single character. Bytes, which will return, I think that takes an argument with how many bytes you'd like to read. read bytes until, you can say keep reading until you find this byte, read string, or read string until. So what we could have actually done here is we could have had read string until that, and is it a character? Yeah, read string until will keep on reading until it hits that, that new line there, and then it will stop, which is kind of good because the other way, if we just call read string like this, and then we call input substring, so this code here, what that will do is it will actually read all of this, and then it will just use this part, and all of that gets lost. Read string until, what it does is if this is my internet connection, well, okay, we have our client, and the client will have a buffer, and that buffer will contain everything to a certain, for a certain point. And when I call read, or read string, that will get everything out of the buffer and clear it. If I call read string until, it will only stop here and it will say, okay, just get that out of the buffer and leave everything else in there. So if we get multiple messages at once, so if we had like A, new line B, new line C, new line D, and we called read string, we would get all of this, and if we just process that part, we'd lose the rest of that. But if we had A, new line B, new line C, new line D, and we said read string until new line, we would just take that part here and process that, and we would leave everything else in the buffer for us to process next time. So there are pros and cons to that. If your buffer is filling up faster than you're reading messages out of it, eventually it will get full and your connection will probably get dropped. So there is some motivation for calling read string in one go because it makes sure your buffer never gets filled. But in this example, if Gonzalo was drawing fast enough, chances are we'd start seeing lines would not get drawn because they would be, you know, in B or C or D, and the computer would just throw them out. He's sending data faster than I'm processing it, so we're going to lose it. Read string until would make sure that I get all of it, but if he's drawing faster than my program is running, then you know, there is a chance that my program would eventually, the connection would get dropped because my buffer would get full and my thing would say, oh, I can't take any more data, I'm bailing. So the write method you can write strings, you can write bytes, you can write integers, whatever you want, you can stick it in there. So if you are using read bytes until or read string until, you can call .clear, which will empty everything out. You can call stop to close all the connections. So if you're the server, so the server will actually deal with multiple connections at once. Calling stop will close them all. Calling disconnect will close one particular client. And you can call IP to get your IP address. So I think there is possibly one coming up that has an example of multiple connections. So just to talk about something else or to sort of expand on this. So this whole thing of, you know, A new line, B new line, C new line, to make sure that we know where one message stops and the next message starts and make sure that we get whole messages and stuff, can be a bit tedious for us to have to take care of all of that. So there's been a number of protocols which have been built on top of various languages to handle all this for us. So I don't have to say, okay, I need to make sure I put in a new line character so I know when one message ends and the next message begins, and make sure that I have a complete message at once, and so on and so forth. So Open Sound Control is one of those, and it's a human readable network protocol, which is kind of nice. So if something goes wrong, I can just print out, you know, tell Open Sound Control, print out the message you received, and I can understand it. It's supported by many languages and devices, and Processing has this OSC P5 library add-in which deals with it. Right, so I'm just going to give an example of where TCP communication might fail and where something like Open Sound Control might be kind of useful. So say I am sending, I have my program which allows me to draw, but it also allows me to send messages. So my drawing, I would send it, as I did before, we send P mouse X, P mouse Y, mouse X, mouse Y, new line character. Cool. The problem is if I send out a ton of these in a row and we have a particularly bad internet connection or what am I doing? 18. Doesn't really matter though. We have a particularly bad internet connection or something, or these are really big, so I'm not sending 4 numbers, but maybe I'm sending you guys an image or a video or whatever. It's fairly likely that these aren't going to come through in an entire chunk. So say I send you guys a picture, which is a megabyte in size, and the largest packet size that I can send is smaller than a megabyte. What will tend to happen is that maybe Gonzalo sends me this message, and he sends it out like this, but because it's got to be broken down into smaller chunks and sent through, I actually only receive that much of it at first. So what's going to happen, I'm going to start reading, assuming that I'm always going to get 4 numbers and then a new line character. So I go, okay, 4 numbers, 1, 2, 3, 4, new line character, that's great, process that. 4 numbers and, oh, okay, so there's actually nothing there. There's no new line character, we've only got 2 numbers. And if I haven't prepared for this in my program, it will crash. And that's fairly common. You know, what you'd normally do in this case is you'd look to see, is there a new line character? If so, I will process it. If there's no new line character, I'll just put it back into the buffer and wait. Because hopefully eventually the rest of that message that Gonzalo sent me will show up and then I can process it. But at this point in time, it's not there. But that's a little bit of extra work that we have to do that we may not want to do. Likewise, what if I want to extend my program now? So not only can we draw and send the drawings to each other, but we can send text messages. So, okay, I'm going to also send hello as just a string hello, so I know that, you know, I'm sending this message and that's going to pop up on someone's screen. So then if I send these 2 messages together, so now I've got 10, 10, 12, 10, new line, hello, new line. So I'm like, okay, well, let's grab everything to the new line, and that's a drawing command, that's fine. And the second one, I'll grab this, and that's a drawing command. Oh, no, it's not, because it doesn't have 4 numbers, so what am I supposed to do? But then what if, you know, Gonzalo's helping me, and I'm like, how do I send this message? And he's like, oh, well, okay, you know, to send the message, type in 8, 10, 6, 10. And then all of a sudden I say, well, okay, hold on, what's going on here? Because I actually have these 4 numbers, but it's in a text message. Am I supposed to treat these like these numbers? Or am I? So it suddenly starts getting quite difficult to know when we're dealing with more than one data type, what are we actually seeing here? Am I missing something? Is there supposed to be a new line character in there and this is actually supposed to be this? Or is that supposed to be like that? So it becomes quite confusing, and these are all if you're writing your own network communication stuff, this is the sort of stuff you have to do. So for my company, we recently did some installation stuff, and you could do some stuff on your phone and then you could send it to a display. And we had huge amounts of drama with this. And it was always edge cases like somebody's on their phone and their internet connection drops out and half the message gets sent, but the other half doesn't. And then the server's like sitting there waiting for the rest of the message to come and it never does, or it gets sent and then the person reconnects because their internet connection or their network connection has dropped out and then come back. But all the middle of this message, so there's been a bunch of middle got sent where they had no network connection, so we end up seeing this and we're like, well, there's a bunch of stuff missing in here, I don't know what's going. So this was a real nightmare to work around and took a long time. There's probably still bugs in there that only very seldom show up. So what Open Sound Control is, it's basically is a way of basically encoding a whole bunch of this stuff in a way that is readable by humans. It's industry standard, so it can be it can communicate with a number of things. It's called Open Sound Control because originally, from my understanding, it was dealt for dealing with MIDI devices. So sound desks, for example, if you had a sound desk in a recording studio and you slid the things up, the sound desk would be able to communicate with the computer in Open Sound Control so that as you adjusted things on the desk, it would update the computer and vice versa. So it was written it's not the fastest thing because it's got all this overhead in it, but it's human readable, so you can, if things go wrong, you can read it. It supports all the stuff, so it will tell you, I have 4 integers in here. I have a piece of text and some integers, so that you know when you're reading it that you're getting what you're expecting. It will do stuff like automatically what is known as delimiting the packet. So I know if there is a message waiting for me, it is a complete message, it is valid, it is correct, it has everything in it that it should have. I don't have to say, oh, is this only half the message, or only half the message gets sent, and so on and so forth. So open sound control is built into the processing, oh God, where are we? Input library as OSC P5. And interestingly enough, I'm pretty sure that's the same guy who did Control P5, which is probably where the P5 comes from actually. And again, has a bunch of examples. Probably gonna have to restart processing to access them, unfortunately. Sorry, just bear with me 1 second. Examples. Okay, so down in contributed libraries, OSC P5, you'll see there's a whole bunch of different examples in there. But let's have a look at OSC P5 message. Okay, let's refresh my memory how this works. Cool. Okay, so what happens in here in this example is we have OSC P5, which is the class and the object for OSC P5, and then we have what is my net address, which is the, so OSC P5 is the server effectively, and net address is the client. I don't know why they chose those names for this, but that's what it is. So we're going to set up an OSC P5 server. Again, looks exactly like the previous server. The name's different, but this and the port. And then my remote location is a net address, and the net address takes the IP address and the port to connect to. So in this case, before we had 2 separate programs, a client and a server which is running. This OSC P5 has both of them running in the same program. So it sets up a server, and then it sets up a client, and it connects the client to the server. Then in mouse press, so when I click on the screen, it creates a new OSC message. So before in our net stuff with server and client, we just wrote .write. Here what we do is we create a new OSC message, and we give it a title. I can't remember what exactly this is called. There is a special name for it. Oh, address pattern, sorry, that's it. So a new address pattern, which tells me what it is. So if I was doing my example before of I want to send drawing data, but I want to send message data, I could have this as drawing. And that just allows me to tell which kind of message it is, drawing or is it text. It doesn't mean anything to the computer, it's for us to determine what's going to be in there. And then in my message, what we can do is we can add a bunch of stuff. So we can add an integer, we can add a float, we can add some text, we can add a byte array, we can add an int array. And what we do is we call OSC P5 send, and we're going to send that message to the remote location. So we're sending it. So in this case, the OSC P5 is acting as the server, but it's also allowing us to send this message to the remote location. So OSC P5 has a function called OSC event, and that occurs when we receive a message. So before we, in the draw method, we would check .available. Here we get an OSC event when that message when we receive a message, and that will return, or that will have the OSC message as a variable. In this case, what we're doing is we're printing out received an address message. The address pattern, so OSC.message.address pattern, will be the pattern or the string that we give it when we create the message, and then we're printing out the type tag. So for reference, we're creating a new message with the pattern drawing. We're adding an integer, a floating point number, a string, a byte array, and an array of 4 integers. We send that out, And then in our message, we're going to print out received an OSC message. We're going to print out the pattern we received, ADDR pattern, which is drawing, so ADDR pattern test. And then we're printing out what's known as the type tag. So what the type tag is it's basically a list of types of all the arguments that have been added to the message. So you can see here it's IFS, B, I. So I stands for int, so what it's saying is the first thing in the message is an int. The second thing in the message is a float. The third thing in the message is a string. The fourth thing in the message is I'm not sure why, but a byte array in this case is just represented by a B. And then finally there's an array of 4 integers. So 1, 2, 3, 4, 1, 2, 3, 4. So we've basically, through doing this, we can see what type of message it is. It's a drawing message, and what sort of arguments it has. So an integer, a float, a string, a byte, and 4 arrays. So we can also get those individual arguments out, and we do that by calling the message.get. So if I wanted to say print out what the first type is, first argument rather, we could say the OSC message.get 0. And if I print that out, click, oops, that has not worked. Why did that not work? Let's try that instead. Yep, so we call .get to get the argument itself. And then we have to call .int value or .float value or .byte value or whatever to make sure that it's in the right format. I thought we could just call .get 0, but apparently that doesn't work. So in this case, I know the first argument is an integer. So I say the OSC message.get 0 and convert that to an int. And that will return the first argument as 1, 2, 3, which if I look up here was the first message which was sent. If I wanted to get well, obviously the second will be get 1. And we know that that is a float, so we can say float value. And then when I click, first value is 1, 2, 3, second value is 12.34, and so on and so forth. So there is another example which shows this a bit better, which is OSC argument, and works in a similar way. So in this case, rather than creating an OSC message, we can actually just put it all in. There's an overload for the OSC P5 send, which takes the first argument will be the address pattern. The second will be an array of objects. So object is a special class in processing in Java, which everything else inherits of. So every class in processing of Java is an object at its base level. So it's a new object with an integer, a float, and a string, and it's sending that to my remote location. And then in this case, it's going to check to see is the address pattern test. If it is, it's going to check that the tag type is IFS, so it's got an integer, then a float, then a string. So is the type tag IFS? And if so, then it's going to get the first one, convert it to an int, get the second argument, convert it to a float, third argument, convert it to a string, and then it's going to print out received an OSC message test with type tag IFS. And the values are 1, 2.0, and test string. And otherwise, if it receives a message that it wasn't expecting, it'll print out the address pattern and the type tag. So if I change this to, instead of test being test2, you'll see it'll just say receive an OS message with the address pattern test2 type tag IFS. So here we've got a little bit of thing we can actually check. Is the message we received a test? If so, does it have the right type tag? If so, get the data. So we can sort of very easily work around these cases where maybe some data got dropped. Is the data still in the right format? Is this what we were expecting? And Yeah, so that's OSCP5. Create the server, create the client, create a message, and then call OSCP5 send message remote to send it. And for the receiving the messages, you get an event. The address pattern will get you this address. The type tag will tell you the list of types that have been added, and get index.intValue.floatValue.string value will get you those arguments back out. And the very last slide for this part of the course is just talking about serial communication. So everything we've been talking about so far has been networking, so communicating from one computer to another. But there are other methods of communicating. So one we're going to look at when we get to the Arduino side of things is serial communication. So that is your computer communicating with a device, or an Arduino, or it could be a printer, or it could be a whole range of things. So serial communication is used for communicating between a PC and peripherals. It used to be very common, becoming less common these days with things like USB, but a lot of devices actually these days, USB runs serial over USB. So you get your the cables for them used to look like this. So this is a serial cable, so you don't really see them much anymore. But these days, things like the Arduino, you can still get Arduinos which have a plug or socket which looks like this. You can plug them via serial, but most of them these days are USB. However, they still run the same communication protocol, which is RS-232 over USB. So when you plug it in, it pops up in your computer's device manager as being USB over serial, because it's still using the same communication protocol. So the old serial stuff was low speed. It had the large connectors. So these things, well, they're about that big. On modern laptops like mine, they just literally didn't have space for them anymore, so they got rid of them. And they could have a large voltage swing as well, so you always ran the risk you plug your computer in that it might fry your computer, or your computer might fry the device. USB is, especially USB 3, is very fast, quite small connectors, and even these days, like this sort of USB 3 type connection are even smaller than the old style ones, and they have very defined, like for a device to get USB certification, it has to only draw this much power, it has to only produce this much power, and so on and so forth. So USB is a lot safer. But oftentimes for things like Arduino and other devices, they still actually use serial communication over that. So whether you're using the old DB9 connectors or USB, it's still the same. And they're used for communication with Arduino. So when Niels talks about that, he will talk about communicating with your Arduino over, he won't be using processing, but he'll be developing on Arduino, but he'll be talking about serial communication from the Arduino. So you can actually write a processing sketch which uses serial. You can see in here, import library serial and examples serial, which has, so you can actually have a processing thing which communicates with an Arduino and vice versa. And I think there might be an example, I'll check with him, but I might ask him if he can whip up a simple processing example to illustrate that. So you push a button on your Arduino and it changes the background color in your processing example or something. So you're having this communication between a piece of software you wrote and a piece of hardware you've built. Otherwise, that is it for today's lecture and for processing themes. So next week we're going to be moving into graphics, which will sort of help segue us between processing and Unity. Any questions? No? All right, good luck getting your assignments done. And yeah, no lectures next week because you have your thesis week. I will still be around if anyone has any questions, although